Okay, so I'm presenting joint work with Paul Paris on the Bisimulation finiteness problem on for pushdown systems, and the main result is that this problem is elementary. Yes, now I have the possibility to share my screen, which should now work, I guess, although not. So, okay, this is the title slide. So let me just briefly summarize the problem that we have been studying. So it's the following decision problem. You're given a pushdown system, nothing but a pushdown automaton, and a configuration, some initial configuration that can, without loss of generality, just consist of one stack symbol. And the question to decide is whether in this infinite transition system that is induced by this automaton, whether this initial configuration is Bisimulation equivalent to some state of a finite system. So is it Bisimulation finite, so to say? And this problem has been shown to be decidable a few years ago by Peter Janschar. So essentially by reducing the Bisimulation finiteness problem to the Bisimulation equivalence problem for pushdown systems. And recently, this was a Turing reduction, and recently the complexity upper bound has been proven for the Bisimulation equivalence problem, namely Ackermann by Schmitz and Janschar last year at LICS. And therefore, the state of the art is essentially that today that Bisimulation finiteness of pushdown systems is in Ackermann, so it's decidable but has an Ackermann complexity. So, in fact, when we look at this proof of Janschar, what has been done is that there are oracle calls happening to this Bisimulation equivalence problem, and as we know this year, we know that the Bisimulation equivalence problem is Ackermann complete, so to say. Yeah, so by using this approach of Janschar, one can essentially not improve the complexity of this problem. And okay, what is important to state in this problem is that the finite system is not part of the input. Okay, so you're just given the pushdown automaton, initial configuration, you ask the existence of a finite system. This is somewhat different to the following problem. When the finite system is part of the input, the problem is much easier and is very computationally easier. And it has been shown in 2010 by Kuchera and Meyer that that if the finite system is part of the input, then the question, given the pushdown system and this finite system, is the finite system bisimilar to the pushdown configuration? This problem itself is p-space complete. Okay, so let me come to the main results. We've shown that this problem, so the Bisimulation finiteness problem of pushdown systems, is elementary. And in fact, we analyzed the complexity precisely and derived an upper bound that is 6-fold exponential in the size of this input pushdown system. So generally speaking, the pushdown, well, the proof strategy is quite simple. So what you do is, what we prove is essentially that if such a PDA, say of input size n, is bisimilar at all to a finite system, then we know that there is already a finite system that whose size is at most 6-fold exponentially upper bounded in the description size of the input pushdown system. And so this is like a kind of a small model property that we show. And once having shown this small model property, in a sense, it's then the rest of the proof for obtaining an elementary algorithm is quite simple. You enumerate all finitely many, elementarily many finite systems of at most elementary size, and each of them you test for bisimulation equivalence. So you test whether you go through all of them and test whether the input pushdown system is bisimilar to all the finitely many systems you've enumerated using the p-space upper bound that I have mentioned on the previous slide by Kuchera and Meyer. Okay, so that is our main result, and so it's kind of small model property. And if you have never thought about this problem and have perhaps heard of it for the first time, in fact, when one is concerned about an elementary bound, if you want to improve the complexity of this problem, the computational complexity, all you need to show is that if a bisimulation finite pushdown system, if a pushdown system is bisimulation finite, there's a small finite system, yes, in terms of the presentation size of the pushdown system. And then you can study this kind of descriptive complexity problem. Yes, and then this is another kind of problem. And well, for this kind of problem, we only know, like so far, an exponential lower bound. Yes, so a pushdown. In other words, to date, we do not know a family of pushdown systems of size n, or that are by simulation finite by construction, but that can contain more than exponentially many by simulation classes. Yeah? So this is a problem that is one can study without ever having had a look at this problem before. So yes, so of course the next step would be to determine the precise complexity. The problem is known to be x time hard, and yeah, that would be, I would assume. Well, I think that the problem is complete for a deterministic exponential time, but yeah, quite some work to be done. Okay, thanks.
Okay, thank you. Sven, do you want to arrange the questions, or shall I?
You can read them in the order that is there, or?
Okay, so so we have some questions on the Slack. We have a question from Lee. So is Lee here? If no, I will read it. So Lee wrote, "Thanks for the interesting talk. I still have a question about it. In my opinion, the difficulty of this work is to prove that the infinite configuration is by simulation finite. On the slide with the pink block, I wonder, how is that theorem important for proving by simulation finiteness? Are there more types of infinity needed to be taken care of?" So the slide with the pink block is from the full.
Yes, I can just
so.
show that 1 second. Sorry, let me just.
The question is also on the chat.
Okay, let's just have a look. Yeah, just I don't have the chat open. Sorry. So can you just repeat please repeat the last part of the question?
The question was that how is the theorem from the pink block, how is it important from proving by simulation finiteness? Are there more types of infinity needed to be taken care of?
So
the question is also on chat, on our chat in the Zoom.
Yes, I can. Problem opening this chat. So what is the main technical theorem state that if so essentially this part, well, this slide, this pink slide essentially tells you that it more or less, if one is interested in improving the complexity of this problem, so to say, it just boils down to analyzing very particular configurations and just to analyze a very particular sequence of configurations, namely that if you start in some initial configuration when you observe that if your configurations that you reach are sufficiently large syntactically, then if they're sufficiently large, then you can pump some topmost parts, so to say, and all that you need to study is just a problem pumping this topmost part. Okay, you can do it as often as you want. It gives rise to an infinite sequence of configurations, and it's somewhat of a sub-problem, yes, that to decide whether for this topmost part that you can pump, there exists infinitely many bisimulation classes, and for these kind of classes of infinite state systems, like pushdown systems, well, essentially this kind of subproblem is more or less equivalent to this kind of subproblem is so to say decisive to study. Okay, so it is kind of the core problem of analyzing if one is interested in improving any kind of upper bound. Of course, this such kind of properties that if you're syntactically sufficiently large, you can pump something. These kind of properties exist for various classes of infinite state systems. Therefore, yes, this result can be likely extended to further classes of infinite state systems. So my answer is this is the decisive problem, and that's the main thing to be studied for any kind of infinite state systems that have some kind of pumping property.
Thank you. A question from Sven. So Sven, you are here. You can read it.
I think it has in part been answered. So my first question was, in the full talk also you have the size of the system given as S of n, right?
Yes, yes.
And that gives you you have a lower bound on what the size of the system is, but that doesn't give you a lower bound on the complexity of the bisimulation finiteness problem, right?
Exactly, yes.
So my second question would have been, if you have an idea, since you want to determine the exact complexity, how to get lower bounds for complexity. But if I understood correctly, you conjecture that it's exponential time complete, and
yes,
there you already have a lower bound. Is that right?
Exactly. So you perfectly answered the question already in a sense. Yes. So this slide was, or this kind of growth function that we study here is essentially how succinct can a pushdown system be, or say a pushdown system of presentation size n, how many that is bisimulation finite by construction, how many finitely many bisimulation classes can it have? Like you can study this kind of descriptive complexity function. And one thing what we show is that this function is elementally bounded, and any upper bound improvement on this function gives a better complexity upper bounds for the decision problem. For the lower bound, if you want to improve the lower bound, you automatically then need to improve the lower bound of this descriptive complexity function. However, if you're able to show that this descriptive complexity function S, yes, is say at least fourfold exponentially lower bounded, where it's lower bound fourfold exponentially, it doesn't have immediate consequence that the problem is like say 4x time hard or something. Yes, so only an upper bound on this function gives immediate consequences on the elementary.
Okay. How was the lower bound, the existing lower bound, proved?
Say on the you mean the descriptive complexity
Decision problem.
Yes. Yeah, that's somewhat really funny. Yes, so it's the most obvious kind of it's a standard kind of lower bound is namely that you can construct a pushdown system, say with n stack symbols. Yes, here I have shown it at x1 to xn. That just behaves, that if you look at the transition system induced by this pushdown system, it just uses a path of length 2 to the n-1, okay, by simply using this kind of doubling trick. Yes, so if you have n such symbols and x1 is pushing 2 x2s and x2 is pushing 2 x3s and so on, if you observe like the transition system that is induced by these n rules, you get a path of length 2 to the n-1. That's like a kind of a witness that, for instance, that there are exponentially that there are exponential. Yes, it's also used for like a p-time lower bound for the non-emptiness problem of pushdown.
Okay, so let's go on. So there is a question from Anka, but before that, for the question about the X time versus next time, since we are already dealing with it.
Yes.
So do you conjecture it's deterministic X time or non-deterministic X time?
Deterministic X time. So something that I did mention, I think, in the last part in my video, but not probably enough in retrospect, is that this problem is known to be X time hard, and this was shown by Meyer and Silva around 2002. And the proof goes like that: you essentially construct a bisimulation finite PDA that only takes the topmost n stack symbols into account, so to say, and you kind of reduce from the emptiness problem for the halting problem of an alternating.
I see. Okay, so Anka, your question?
So X time, deterministic X time.
Yeah, Anka, do you want to ask your question?
Sorry, yeah. So it's just about, I was wondering whether your approach with the pumping, whether it has some chances to work also for epsilon transitions or not.
So the decidability of, so in this, important to mention that in this model, so to say, we do not have any epsilon transitions. And if you then ask, for instance, for weak bisimulation finiteness, so to say, this problem is not known to be decidable yet. So if you have epsilon transitions, the problem is not known to be decidable, and it's an interesting open problem. But what we're using in this proof mainly is that using the finite out degree, yes, that the pushdown system as an explicit finite out degree. Yeah. So the problem is still open, yes, in the presence of epsilon transitions.
So we have just, we thought we will end with in 12 minutes, but let's have the last question here. Antonin asks, what about weak and branching bisimilarity?
Yeah, so that's essentially, so the question whether so if you quotient, well, if you look at the transition system that is induced by an PDA with epsilon transitions, that's the same. So weak, that's exactly the same question as before. Yeah. So the presence of so every PDA that has epsilon transitions is weakly bisimilar to a prefix organizable graph, and so we can ask the same kind of questions for prefix organizable graphs. Yes, given a prefix organizable graph, does it have a finitely many bisimulation classes? And that's equivalent to asking weak bisimulation of a PDA that has epsilon transitions, and this problem is still not known to be decidable. By the way, the bisimulation equivalence problem for this model with epsilon transitions is highly undecidable. Yes, it's sigma 1 complete. So.
Okay, so the very last one from Igor. Igor, will you ask it?
Yeah, I wonder, so I was very intrigued by your SN function, which is a good subject to study. So if you take trace equivalence instead of bisimulation equivalence in this definition, do you have better estimates?
So it's known by a result by Fisher, I think, and Peterson. In the 70s, there was a result that this function S of n is double exponentially lower bounded if you look at deterministic pushdown automata having epsilon transitions. Or deterministic pushdown automata with epsilon transitions. So the presence of epsilon transitions gives you some kind of succinctness gain, yes, that is not known for this kind of orthogonal problem, yes, when you look at bisimulation finiteness of epsilon free PDA. But for deterministic pushdown systems, this function S is well known, upper and lower bounded. It's double exponential in the input size. And so for deterministic pushdown automata, bisimulation finiteness is known to be deterministic exponential time, and is only known to be hard for deterministic polynomial time.
Okay, let's move on to next paper. So it's A5B, the complexity of reachability in affine vector addition systems with states. So Mikhail, you are giving it?
Yes. Is my screen seen?
First, thank you, Stefan, and thanks for all the questions and answers.
Thanks.
Is my screen seen?
Mm-hmm.
Yeah, good. So, hello, I'm Michael Raskin, and we with Michael Blunden present our results on complexity of matrix class reachability for affine extensions of vector addition systems. So the affine extensions are defined in the pretty standard way as before, that normally we have states and transitions are additions of vectors, and now we say that indeed instead of pure translations or pure addition of vectors, we also allow affine transformations. And then we consider as the integer extension in the sense that we have not necessarily natural numbers as counter values, but arbitrary integers as counter values. And it turns out that there were some known cases which were p-space or undecidable classes of affine extensions of integer vector addition systems. And in our work, we answer what are the possible complexity values for a matrix class. So a matrix class should be corresponding to the normal notion of an operation. We pick to which counters we apply the operation, and then in which order, and apply this operation to the counters. And so To formalize, it turned out that we need to say that a matrix class for a affine vector addition system is closed under addition unaffected coordinates and conjugation by coordinate permutations. These two claims correspond to choosing to which counters to apply and to choosing in which order to apply. And then we have two main theorems. First is the trichotomy for complexity, that an integer affine vector addition system reachability problem can be NP complete if we have only reset matrices. That means diagonal matrices of zeros and ones. P-space complete otherwise if we either only have pseudo transfer or only pseudo copy matrices, which means 0, 0, 1, -1 matrices, which basically behave like transfer operation or copy operation in the sense that either each row or each column has exactly one, or has at most one non-zero element. And in all other cases, the reachability problem is undecidable. And for a natural affine vector addition system without the integer extension, we confirm the folklore saying that any interesting extension has undecidable reachability, saying that the only decidable reachability is in the case that the matrix class doesn't contain anything but permutations. And yeah, in the future work, we mentioned that for individual instances of that VASS, arbitrary complexity seems to be possible, but it's not yet fully written up. And for a fixed matrix monoid, it's an open problem. What is the possible range of complexities, or maybe more precisely, what is the possible set of intermediate complexities? Because obviously NP inside complexity inside NP and undecidable are possible. So it's not the range; it's what are intermediate steps that are possible. Okay, that's it for the overview. And now the questions.
Yeah, so I actually posted a question on Slack. So there is the field of descriptive complexity, where there is characterization of complexity classes according to, yes, by the type of logic needed to express the language in them. So can you say something about this? Because you have a characterization. So can you say something about the expressive power of pseudo-transfer matrices?
Well, yeah, thanks for the question. Yeah, we have seen it on the Slack and even briefly discussed with my co-author whether we have something interesting to say, but probably not. In the following sense, that's depending on what we want to express. Do we want to express logically the reachability relation or the language of taking transitions? It's, of course, it's slightly different problems, but in both cases, we have this problem that it's basically what we get is at least p-space hard, in the sense of reachability that we have a very simply defined subset, which is already p-space hard. And in the case of the language of taking transitions, it is pretty easy to set up a VASS where, well, we model a Turing machine as usual in the p-space hardness proofs. So it's easy to set up a VASS where initially we just fill the tape. And then the language of taking transitions will have this property that log space machine can take the word in the language and cut out a part, and then the cut out part by log space machine is exactly like the image is exactly some p-space hard language. And therefore, well, in both cases, we have something very expressive which reaches p-space complexity, and we don't have any good, precise characterization of the logical properties of these languages.
Thank you. And Dimitri?
Yeah, I can ask. So, Michael, I mean, for usual vector addition systems, there's been quite a lot of research about, low-dimensional cases, and they are becoming somehow, I think, increasingly more important in the context of the recent, kind of non-elementary lower bounds. So, and I was just wondering, whether a lot can be said in your setting for matrices of low order, low size, like 2 times 2, 3 times 3, and so on. So maybe if you also add some of the restrictions that you've got, or maybe without them.
Well, we didn't study the precise behavior in the truly low dimensions, like 2 times 2 and 3 times 3. On the other hand, in the previous work, actually, I think it's under review still, but in a larger collective of co-authors, we have written this previous stuff about specific vector addition systems, affine vector addition systems. There is a single matrix that we can use in a reasonably large but finite vector addition system, which already yields undecidability. And basically, we can model the Gilbert stem. We can model the Matiasiewicz's construction for undecidability of Diophantine equations with a single matrix. So it all ends up at some not very large dimension.
So when you say undecidability here, you mean for the reachability question? Because I mean, people have studied matrices from, let's say, the mortality perspective, and there they hit decidability quite soon, undecidability quite soon as well.
Yeah, for specific reachability properties, it's a finite. It's a single matrix where reachability is already undecidable.
I see. So the input to the problem would be just a pair of vectors. Can you go from here to here?
Yes.
Okay. Thank you.
Okay, thank you. And last question from Igor.
Okay, thank you. Thank you for a very nice result. I wonder, I read it a little bit negatively in a sense that most of the classes are undecidable. So if you can you weaken the notion of a class of matrices, like adding natural rows, coordinates, I think it's very natural, but the other condition you have, maybe it can be weakened to get some more positive results?
Basically, the other condition is also pretty natural, because when we talk about, for example, addition with, vector addition system plus copies, we usually allow copies in both directions. And so if we allow adding the rows, then there is a question, well, what exactly we can do? Because then basically, it's pretty, I mean, it doesn't correspond to a natural, there is no clear way. Okay, if we just allow inserting rows in arbitrary places, then then what we have say, because basically the point is that as soon as we have doubling, we can use post correspondence problem, and it doesn't really depend. If you have just a single doubling, it doesn't really depend on do we have permutations of rows. If we have just arbitrary large element in the matrix, if it at any matrix in the class, then in the current setting, it's pretty easy to explain why we can apply it in such a way that we get something which behaves like doubling. If we drop the permutations, it probably become technically harder, but I would really expect that, well, we might get some positive result, but it would be for a weird class where basically the value falls down all the time. and notice that again, that you also need to avoid the other trap, that even if the value falls down all the time, you need to avoid another trap where the single matrix, which is already undecidable when you model the polynomial evaluation. So I wouldn't expect anything, you know, natural and interesting, maybe something interesting, maybe something natural, but not both, I think.
Okay, thank you. And we are moving on to the next paper. So
Yes.
Antonin, you are presenting it, right?
Yes, so can you hear me?
Yes.
Okay, good. So I try to share my screen with you. Okay. So can you see it?
Mm-hmm.
Okay, good. So let me start. So the paper is about efficient analysis of VASS termination complexity. So let me remind you about the results. So first, what is a VASS? It is the standard definition of vector addition systems with states. So we have control states and transitions that are labeled by counter updates. So in our complexity estimations, we assume that the counter updates are encoded in binary. So here is a simple example of a two-dimensional VASS. So I believe that you know this model, or you can guess what it does. So we further assume that the set of control states is divided into two subsets of angelic and demonic control states. The states are controlled by two players, the demon and the angel. And the goal of the demon is to prolong the computation as much as possible, while the angel aims at shortening the computation as much as possible. So the computation stops when some of the counters reaches a negative value. So computation intuitively starts in some initial configuration for some initial control state and some initial counter values. And then the two players determine a path, a computation in this graph. And you can view it as a game with of two players, a turn-based game of two players with opposite objectives. And these games are known to be determined in the sense that it's sub-equality holds and defines the what we call termination value of a given configuration. So intuitively, this is the number, the length of the computation obtained from this initial configuration if both players play optimally. So in general, this can also be infinite because it may happen that the angel cannot prevent the demon from creating an infinite computation. And the termination complexity is a function which to every integer n assigns the maximum value of a configuration where all the counter values, the initial counter values, are bounded by the n. So this is the termination complexity. And what we do, we study the asymptotic behavior of this termination complexity. And the measure we use is so the complexity measure we use are these GK classes. So let me introduce them. So first I need to define the more or less standard hierarchy of fast-growing functions. So for our purpose, it is convenient to fix first a linear function, then quadratic, then exponential, singly exponential function. And then we go on in the usual way. So fk plus 1 is defined as the composition of the previous function applied to the n. So if you look at this, well, okay, so and this GK class, the GK stands for Grzegorczyk because this is tightly related to the standard Grzegorczyk hierarchy of functions. So this GK is the class of all functions which are bounded by some composition of this fk function. So this mu has to be a constant. So if you look at this, then if you compose linear functions constantly many times, you obtain just a linear function. If you compose quadratic function constantly many times, you get an arbitrary, so a polynomial of an arbitrary degree. And if you compose this, you get an elementary function. So this is how these G classes look like. And our theorem says the following. So if we are given a k, then the problem whether the termination complexity function of a given VASS belongs to the class GK is decidable in polynomial time for demonic VASS. That is, for those VASS, there is only one player, the demon, who wants to prolong the computation. And we also have a kind of get saying that if the termination complexity does not belong to the class GK, then it grows at least as fast as the generator of the next class, or the fk plus 1 function. And we also have a similar result for VASS games, where the same problem becomes NP complete. Instead of being solvable in polynomial time, it is NP complete, and we have the same type of gap. So this is it. That's the result. So
thank you very much. So any questions?
I can have one online without posting.
Go ahead.
Why this definition of termination? So terminating games when you hit 0. Of course, one can think about reachability, but I think there were all results saying that then it's quickly undecidable. What is the motivation for terminating games?
So the motivation, I mean, originally the problem of analyzing the VASS termination complexity was considered mainly for demonic VASS. And if you have just a demonic VASS, then it doesn't really make sense. That doesn't make a difference whether you say that the configuration reaches a negative value in some counter or that the configuration is simply blocked, that there's no computational step possible from that configuration. So the motivation for this comes from the program analysis. So since we wanted to consider also games, a natural generalization of this concept is to stop the computation when you hit the negative value.
But I think there were some results saying that the games in general, when you consider reachability of even upper closed set, are undecidable, no?
Could be. So yeah, I mean, if you are thinking about generalizing this theorem by saying that we want to, reach a certain configuration, which is, so to say, terminal and belongs to some class of terminal configuration, yeah, then the results might be different. And also the behavior of the termination complexity might be different, because here, if you increase the size, the initial size of the counters, the computation, the complexity can only grow. But if you have more complicated set of final configuration, this is not necessarily monotonic, and there are some problems. So yeah, this is actually a different problem if you have this.
Let's continue. Meanwhile, we have 2 more questions from Sven.
Okay.
Yes.
Your question?
Yeah. So your 2 theorems state that if the termination complexity does not fall into one of these GK classes, then there exists a constant C such that some property holds. Can you tell us a bit how this constant is determined and how difficult that is?
Well, I mean, we have not evaluated this constant explicitly because this would be a pain. In principle, it is doable because, I mean, all we do in the construction is a sequence of constructive steps. So in a way, we should be able to determine the constant C, only that this will be technically complicated. So I cannot give a precise answer to your question. All I can say that if you really wish, then the constant should be computable, I mean, by simply analyzing the complexity of our constructions.
Okay, good. Thank you.
Okay, so Anka, you want some motivation? So
yeah, I want some motivation. So it's somewhat related to Igor's question. So okay, I see the demonic case is relevant for program analysis because you're looking at worst case behaviors. But why do you have the angelic player?
Well, okay, so it is true that originally the problem was studied in the framework of program analysis for these demonic VASS, where you have the worst case behavior. So we added the angelic pair because it appears natural to me. I'm a game theorist, so I like games. And furthermore, there is a classical paper which analyzes, defines different types of non-determinism in program analysis. So this angelic and demonic non-determinism, the terminology is borrowed from this paper. So. Yeah, so the short answer is I do it because I like it. I like games. And I also think that this is sort of natural because, I mean, you have this type of non-determinism used, people in program analysis use it. So, yeah.
So since you said that you like games, one more question. So you said that this setting, VASS games, is closely related to energy, some form of energy games?
Yes, yes, we can view it as an energy game situation.
Okay.
The last question?
Okay, I'm more convinced my question really makes sense, but I wanted to ask you about some example of weird behavior of this game. Like, in which sense it's much more complicated from the only bounding the termination time in the demonic case.
So I'm not sure how to answer your question, what is so weird there. So first of all, I mean, our result, which says that the problem for games is NP complete, really uses the property of these GK classes, that they are closed under function composition. And this fact allows you to prove that essentially the angel who wants to make the computation short, can essentially play in a counterless way. And this is the reason how, this is the way how we establish the NP membership, because you can simply guess the strategy for the angel. It just depends on the control state. So we fix an outgoing transition for every state. But this fails if you have some finer grained hierarchy of complexity classes, for example, the polynomial hierarchy. If you, for example, want just wonder whether the termination complexity is quadratic or not, then it is not even known to be decidable for VASS games. And this problem is piece-based hard. So this shows that, I mean, this idea, the whole approach to this problem we used is not applicable. So there is some kind of weirdness, because in certain situations, if this class, the complexity class you consider is finer, then you must take into account what has happened before, because you might have pumped some of the counters to higher value and then reuse this to pump it even to the higher value and so on. While in these GK classes, this effect is demolished, because this GK class is closed on function composition, so this effect is not so important in our scale.
I see. Thanks.
Okay, thank you very much. Thanks to all the questions, and we proceed to paper number 4.
So I guess it's mine.
Mm-hmm.
So let me share the screen. Moment. Okay, can you see this?
Mm-hmm.
Aha, moment. So maybe I should. Maybe I'll do it in another way. I should maybe start. Sorry. Presentation. Mm-hmm. Okay. Sorry, I'm having.
That's okay.
I hope you now see this. Okay. So I just briefly summarize, recall what we have done. I'm Wojtek Czerwiński, and that's a joint work with Georg Zeche. So very briefly, first notion of separability, that if we have two sets or two languages, K and L, we say that set S separates them if the situation is like here. So S includes K and is disjoint from L. And the question of regular separability is the following one. You are given K and L, and you ask whether there exists some S, which is regular. Yes, so when we say K and L are regular separable, if there is some regular language S which separates them. And our question which we consider is the following one. You are given two languages K and L, which are VASS languages, defined in a standard way. So you just have a VASS, such that transitions are labeled by some letters. What is maybe important to emphasize, we consider VASS languages where acceptance condition is given by a single configuration, not by a state, but by a configuration. So it's like a reachability language, not a coverability language. And then you ask, okay, are these two languages regular separable? So this problem is still open, and we think it's very challenging. So in particular, it's at least as hard as reachability checking for VASSes, and probably it's harder. But our result is our main result is the following. So we have solved some cases of that. Some cases were known before, but we have pushed the limit a bit further. So we have shown that regular separability problem is decidable in the following situation: when on one side you have a VASS language, and on the other side you have a VASS language from one of the subclasses. And we have solved it in these three cases. So if on one side you have a one-dimensional VASS language, so language recognized by one-dimensional VASS, or second case, VASS in which acceptance is defined not by configuration but by state. So it's much simpler language. And in the third case, if the second language is described by so-called integer VASS, So integer VASS is a VASS in which you allow a run for going below 0. So it's also known that every Z VASS language is a VASS language. So this is our main result, but we think that our main contribution is the uniform technique, and we hope that this technique can allow for future progress, and also is interesting in its own. So maybe just one last slide, an example of this technique. So we have shown that, for example, if you consider VASS versus integer VASS, you can focus on a very special fixed Z VASS. So you can fix one of the languages, and then we fix a special language Zn of which is a Z VASS language. This is just maybe recall. I will not go into details. And our lemma was like that we have characterized which regular languages have empty intersection with our fixed Z VASS language. So these are the potential separators. So if R is a regular language, then R has empty intersection with this our fixed Z VASS language Z. And if R is included in a finite union of some basic languages, which we know the form of, so modulo and drift languages. Okay, and I think that's it for now. Now I would be happy to listen to the questions.
So thank you, and we already have one question. So how do you pronounce your first name? Tugral?
Togro.
Okay, go ahead.
So the question is really to reduce the problem to separating the given VASS and this special VASS Zn, and then you classify, you characterize all the separators you need to consider. My question really was, so what do the original separators look like? The regular languages that separate the VASS from the given Z VASS. Do they resemble the modulo and drift languages?
So in some sense, they cannot do this, because observe that VASS languages are more general than regular, and Z VASS as well. So if you ask whether, for example, language L and complement of language L can be separated by a regular language, where L is a regular language, then the only separator possible is L itself, yeah?
Mm-hmm.
So we could have cases in which there is only one special separator for our two languages, which is a given regular language L. So we have no hope for restricting this class, but in some sense, yes, because you just have kind of we reduced by these rational transductions, which are functions defined by transducers, and you just kind of push back our union of modulo and drift languages via this transducer. But this transducer can implement any rational transduction, and this is where the arbitrary languages come in.
Okay. Yeah, I think the other questions, then that answers them as well. I think this answers like everything I'm the second question as well.
So I've looked at your questions like 5 minutes ago or 10 minutes ago, and so second question, you are right. So I mean, in general, it's as rich as possible, but it's a valid question for the for our lemma, yes? So which regular languages can avoid a canonical VASS language, not canonical Z VASS language? And I can't answer at the moment. I think that should be a much richer class, but I don't see an example at the moment. But maybe what I should say at the moment is that the question whether regular language and a special this canonical VASS language, as you remember, you know what I mean?
Yeah. So
this question is equivalent to VASS reachability, because you can reduce reachability problem of a given VASS to the problem whether a regular language and this special language which has just letters going up and down in every dimension, you can reduce to the intersection of such two languages. So then understanding which regular languages avoid this special language, this should be hard.
I see. Thank you.
And main obstacle, third question, just briefly. I don't know, just we don't understand the structure.
Because you say that the separator, if it exists, is in a finite union of some special languages, so you don't know anything about the size of the union?
So, okay, I was answering the third question by Togrul.
Sorry.
How big becomes the regular separator, in which case?
So if one exists, do you have any idea how big it gets compared to the VASSes that you have?
But you assume the general question like you are given two VASSes, not without assumption. So
no, the VASSes you have in your subclasses. So you have one general VASS and one Z VASS or whatsoever.
So we haven't thought about bounds, but I think it's at least as hard as. So they should also fulfill bounds which come from the reachability algorithm for VASSes. So I guess.
I think we do have an Ackermann lower bound. We do have, so at least for the one-dimensional and for the ZVASS case, we have an example where the separator is Ackermann size, at least.
Okay, so the separator is...
I don't remember if the same example works for coverability, but I'm not sure in that case, but yeah.
And I would think, I don't know whether you agree, Georg, but probably something similar, something like Ackermann upper bound probably would be possible. I mean, that would be
because I think it would be interesting to have small separators. I mean, this is a simple
definitely.
separator, but it's absolutely huge. So, yeah.
I don't think we have an upper bound though, because we use some techniques that enumerate and use Walk quasi-ordering techniques. So I don't think we have an upper bound, by the way.
Okay.
Thanks.
Okay, so this answers also my question. I asked whether you can estimate the size of the separator. So
yeah. So the feeling is that if you are dealing with VASS, you I mean, it cannot be too simple, But what Georg mentioned, I don't remember the proof, but we already have a Ackermann lower bound.
Okay.
Probably
because we use the separability in the commutative case, and that uses Walk quasi-orderings. You remember where you construct these linear sets that are inseparable? And then we don't have any upper bounds.
Okay. So thank you very much. Thanks also for all the questions. And we are in the last talk.
Hi. Yes. I will share my screen now. Can everybody see it?
No.
Yeah, now I guess. Yes. Now I guess. Now I guess you can. Yeah. Okay. Hi, I am A.R. Balasubramanian, and I am here to present my results on complexity of controlled batch sequences over finite subsets of n to the d. Okay, so I'll just jump straight to our results. So the well quasi-order we'll be considering has domain as finite subsets of n to the d, and we will in fact consider two different well quasi-orderings. The first is called the majoring ordering, where we are given two subsets x and y of n to the d, and we say that x is less than or equal to y over the majoring ordering if for all element x in x there is an element y in y such that x is less than or equal to y. So by Hickman's lemma, one can prove that this is in fact a well quasi-ordering. Now, with the second ordering we consider is called the minoring ordering, where we say that the subset x is less than or equal to subset y over the minoring ordering, where if for all y in y, there is an x in x such that x is less than or equal to y. Further, for every subset x of n to the d, every finite subset x of n to the d, we define a norm function, which is just we pick every element x in x, take its norm, the usual norm over n to the d. And further, we also take the cardinality of the subset x, and we take the maximum over all of this. So this norm function maps a subset x to a number in n. Right. So this is a well quasi-ordering. And given any well quasi-ordering with a norm, we can now talk about controlled batch sequences, So what's a controlled bad sequence? It's a bad sequence in the usual sense of a bad sequence in the Bell-Quasi order. And further, the sequence is called G, N0 controlled bad if the norm of x0 is less than equal to n0, the norm of x1 is less than equal to G of n0, and so on. So it just the norm of xi in general is less than equal to G composed with itself I times on n0. So by conic lemma, one can show that we can in fact define given a particular number n0 and given a particular function g and a Bell-Quasi order x, we can define a function which maps these quantities to the maximal length of g, n0 controlled bad sequences. So this we can do by conic lemma. So now we can state our results. So we let g be any primitive recursive function. What we show is that so the length function of g over the majoring ordering is upper bounded by a function in the complexity class f omega to the d minus 1. So this f omega to the d minus 1 represents the fast growing complexity classes as was roughly introduced by Professor Quisera. Further, we also show that this bound is tight. What do we mean by this? We show that for any function g which grows faster than a polynomial, the length function of g over the majoring ordering is lower bounded by a function in this complexity class. Now, our second result is over the minoring ordering, where we show that the length function is upper bounded by a function in the complexity class f omega to the d minus 1 times 2 to the d. Further, we also show that it's lower bounded by a function in f omega to the d minus 1. Unfortunately, we were not able to close the bound, the bound between the lower and upper bounds. Finally, what we do is we use these upper bounds that we derived for both the minoring ordering and the majoring ordering to give some upper bounds on running time for the control state reachability problem for some automata models. So these include the incrementing tree counter automata. So these are roughly counter automata which work over trees, but they can have incremental errors. And two other models of automata which roughly relate to register automata with one registers. So that is it. Thanks.
Thank you. And we have a question by Wojciech, right?
Yes, thank you. So I was always surprised by because you follow the standard line of controlling such a sequence, yes?
Yes.
So it's saying that the, let's say, cave vector or something, it has norm bounded by some function of k.
Yeah.
But usually, and this is what people before also did, and but usually I was also always surprised that this is the way how people do it, because usually you apply this result to, let's say, VASS or other infinite state system, in which, of course, you have these bounds on a norm, but what you moreover you have a very small bound on the difference between two consecutive vectors. Yes.
Yes.
So I wonder if you define a control in such a way that you have a difference between two consecutive vectors are norm of that is bounded by, I don't know, some constant. Does it help? Can it lead to better estimation?
So there is actually this paper by Silva Schmitz in last year's iCalc, if I remember correctly. So where, I mean, as you had said, what he does is he looks at this control sequence where the norm of xi plus 1 is dependent on the norm of xi. So the thing is taken to be that norm of xi plus 1 is not bigger than the norm of xi when you apply this function g, right? So he then considers controlled bad sequences with this definition of a controlled bad sequence, and he actually shows that you can you can get one level less in the fast growing hierarchy with respect to the controlled bad sequence. So in fact, you can actually get better bounds, and he actually uses it to show that this complexity of lossy counter machines is fd minus 1 complete or something. So the complexity of the lossy counter machines is fd minus 1 complete or something like that. So in fact,
I actually meant that you estimate norm of xi minus xi minus 1. So norm of a difference between two consecutive guys.
Ah, okay. That I don't know. Yeah, that I don't know.
Okay, thanks.
Okay, thank you. Dimitri?
So my question was actually originally very close to what Wojtek ended up asking, but I have another one as well. So in the full version of the talk, there are these kind of reductions, which are reflections.
Yes.
But then if you think about this as as an ordering, you can think of forming kind of equivalence classes, right? Where you can reduce there and back again. And I'm just wondering if these are of any significance. Like, you know, maybe for individual sequences or for like classes of sequences.
I don't. So I mean, the whole reason of, or at least the initial motivation for studying these in the form of computer science in this format was to give this upper bound on this coverability models. So I don't know if, I mean, of course, it's an interesting question to study equivalences between these, but I don't know if they have any applications.
Okay, I mean, the reason is quite clear because, I mean, if you think about kind of how, you know, the consequences of the notion of equivalence once you take like polytime reductions, let's say, right? I mean, you get really important equivalence classes. The question is, you know, would you get something here? But yeah, okay, maybe that's...
No, I mean, I agree that it's an interesting question to study, yes.
Okay, thank you. This was a nice talk. Thank you.
Thanks.
Okay, more questions? Okay, so thank you. And thanks to all the speakers. Let's open the microphones and do some clapping for them. And thank you very much, everyone.
Thanks.
Bye.